Thanks, Marat, for allowing me to have this speaking slot. As a few of you may know, I'm an aspiring science fiction writer, and I've got one book out, one full-length novel out, and another one in the oven. I write about the cognitive technology and its possible impact on the future of civilization. And with your indulgence, I'd like to read you a short story I wrote yesterday inspired by the conversations here at the conference. So this is dedicated to all of you. I think I need my reading glasses. Once upon a time, a long time ago, a bunch of molecules hung together on the face of a rock. One day, by some miracle or accident, they formed an autocatalytic set. They worked together to make all the molecules that were part of the group in just the right amounts. Then they found it convenient to leave the rock and live together in a bilipid layer. The first cell was born. The cell learned to divide and multiply. The problems cells had to solve were fairly simple, but as they competed with each other for resources, they became more sophisticated. Molecules on their surface sensed the environment, and molecules inside interacted with each other to process information and adjust their behavior. Some cells learned to talk among themselves using molecules. They organized into groups and decided what jobs to do. Some became bones or muscles or skin. Some cells joined together to become the brain. They used molecules to talk with each other in a new way, processing information about the environment and adjusting the behavior of the animal. The problems the animals had to solve were fairly simple, but as they competed with each other for resources, they became more sophisticated. Some animals learned to talk among their own kind, not only with molecules, but by disturbing the air or manipulating light. They organized into groups and decided what jobs to do. Bees formed hives and ants formed colonies. Humans also formed groups with specialties, held together by the movement of information. What is the moral of this story? Information is the essence of life. It is the alchemy that transforms a glob of matter into a living system. Communication and control are the primary job of the brain. I suggest that this is the correct framework in which to build a high-level theory. There is already a lot of work in this area. In 1948, Norbert Wiener wrote a book in which he coined the term cybernetics. Contrary to the modern bastardization, it is not about computer security, but rather about the control and communication in animals and machines. In 1952, Ross Ashby wrote the book Designed for a Brain. I have not read this book except for the section where he describes a machine called the homeostat. It is essentially a recurrent neural network that adjusts its own weights whenever its outputs drift away from their target values. His ideas could provide a framework in which to understand the homeostatic regulation of synapses within the brain. In 1973, Maturana and Varela wrote the book Autopoiesis in Cognition. They proposed that the necessary movement of information for life to sustain itself is the foundation for high-level cognition. This is the core idea in the story I just told you. Why aren't these people household names, at least among us? Were they wrong, or were they too far ahead of their time? Perhaps a little of both. I offer that when we finally have the grand unified theory of the brain, or gut brain, it will involve the rediscovery of many ideas and theorems from cybernetics. Therefore, it behooves us to become more familiar with that literature. And that's it. I want to now go on to boring stuff. So, the actual topic of my talk is it's good that I'm following on behind Tarek because he set up a lot of the framework about doing computation with memristors. And I'm going to present a small study that we did One particular memristor, we got a tantalum oxide memristor from HP along with a test board that they developed, and unlike Tarek, he presented a lot of the effort in making analytic models of memristors. We sort of went the other direction and did an empirical model. So we took some memristors and did a lot of sampling on them. At first we tried to lock the resistance of the memristor into some known value, apply a voltage pulse, and then read the resistance again. Along the way, we realized that we were doing a lot of effort. We were wasting a lot of data that we could otherwise use. So we developed this random pulse sampling method where basically we took the resistance wherever it was at, applied a random voltage pulse to it, and read it again, and just kept interleaving random voltage pulses and resistance reads. Using this method, we collected over 10 million samples on a single memristor. We did several of these. I think the largest one was up to 20 million samples, and they were collected in less than 24 hours. This is our 10 mega sample set illustrated here. This is actually decimated by a factor of 100, so you're seeing about 100,000 points here. The graph on the right shows a view looking down. It shows the coverage of the pre-pulse resistance and voltage space. You can see some hard diagonal edges in the upper right and lower left of that diagram, and that's where our random pulse regime was limiting the range of the random selection so that it would push the resistance back into its central range. Otherwise, we would destroy the memristor. They're vulnerable to being worn out in bad ways. Okay, we did some analysis on this data set that we collected, binning the resistance and voltage pulses, 100 ohm by 0.1 volt bins. We got the average and standard deviation of all the data points that fell within those bins. And then we used these as a kind of lookup table to model a memristor. So instead of an analytic model, we're simply doing a table lookup every time to simulate what would happen when we apply a voltage pulse. And then we use this to create a perceptron learning arrangement similar to some of the ones that Tarek just described. We used a fixed bias resistor in our simulations. And so this is all software simulation, but this is not a built device. Okay. So we simulated a bias resistor on each column rather than balanced pairs of memristors. One reason to do this is that it cuts down on noise. The memristors are noisy devices, but a conventional resistor would be a less noisy way to get the reference resistance on those columns. I won't go into depth on backprop or the perceptron algorithm, but they're summarized by those 4 equations in that box there. It's noteworthy that the way we calculated the relationship between weight and resistance in our system is given in this equation on the lower left. R bias is the bias resistance, R is the memristor value, and then R out is a resistance that converts the current into voltage at the output block. And then our selected values for R bias and R out are given there. Now, one interesting problem we ran into with this system is that backpropagation is a very sensitive algorithm. It involves small weight changes. If you try to change the weight too quickly, that's equivalent to having too large of a learning rate, and as you know, that destabilizes learning algorithms. And so we kind of run into a limitation here. There is a lower limit below which we cannot converge using this because the precision of it, you simply cannot set the device that precisely. Now, this work, it's okay for a number of learning situations to converge to less than 100%, but we sort of want to learn these Boolean circuits. Now, Tarek is reporting results where he actually fully learned Boolean circuits, but we couldn't achieve that on a simulated crossbar with full noise. So we ended up kind of despairing of the backprop approach. Instead, we came up with this absolutely absurd algorithm, which is basically random walk. This is like the worst possible thing you could do. The basic idea is that if you put a threshold level pulse onto the array, you'll get a small positive movement in the weights. And so we kind of interleave two kinds of steps. In one step, we pulse the entire array in simulation and have it move a small amount. I really need it. Is this the laser? Don't look in it. Beautiful. Okay. So we make small positive steps that just kind of wander through the weight space in the positive direction. Whenever one of the weights saturate, we can hit it with a large negative. Well, okay, I got to get this right because there's a convention that memristor people use. Negative voltages actually increase the resistance and vice versa. So we hit it with a large positive pulse, and it drops the resistance a lot. I neglected to mention something on this previous graph, and that's what we call the cliff. So when we're increasing resistance, we have kind of a fine-grained control, but when we're decreasing resistance, there's a sharp drop off there. These are measured characteristics of the memristor. So this is a very, very hard, any activity in this point is very, very hard to control. And so what our algorithm does is it adapts to that and says, okay, fine, we'll make small negative pulses, which will gradually increase the resistance, and then when we want to decrease one, we just hit it hard and let it go all the way down as far as it can go. It's kind of a random where it ends up, but it tends to be quite a bit larger. So anyways, that's the essence of Lotto. It kind of worked. It only works for small data sets, and but it allowed us to get to 100% on this network. The key point, I think the takeaway message is that we need alternate algorithms. Darisha was mentioning some techniques that she was using in training on the first day, which probably are way better than what we did, and so we need to keep exploring this. But I think it's pretty clear that backprop is not going to scale for memristor crossbars. How much time do I have? 5. Okay. I want to quickly go over something that I talked about last year. There isn't any new updates. I just want to remind you of the existence of our neuroinformatic tool called Into Neurons to Algorithms. We're basically trying to address the problem of having huge amounts of neuroscience information and the difficulty of organizing that into some useful form. That is a problem that a small segment of the neuroscience community called the neuroinformatics community is working on. There's like 1% of neuroscience is called neuroinformatics. And there's a number of different people working on this, including us. Into kind of functions as a modeling language, sort of in the same part of the space as Pine and NeuroML. We conceive of the modeling problem this way. There's a ontology of neural systems put out by the Neuroscience Information Framework. They're kind of like the U.S. Side of neuroinformatics, and their goal is to unify all these different data sets, and so they have this ontology so that everyone can have a consistent language in which they refer to neural parts. And the idea is, you can take all these different parts. Each one of them has some metadata associated with it. Why not think of the set of ODEs that describe the behavior of the part as some of its metadata? And so we've developed a tool and language that lets you do that. And this is an example of Huxley model. Almost everything's on here except the potassium channel, which I left off the slide because it just won't fit. And our tool knows how to do a kind of an object-oriented composition of these. It has inheritance, inclusion. It has the ability to take these parts and replicate them many times over, so you can essentially create populations of neurons. And then I'm just going to quickly show you the results when we compile this. We can put it in two forms. One is simply straight C++ code. And the other is what's called Zeiss, which is kind of like a parallel version of Zeiss. I mean, Spice. Sorry, I'm getting messed up here. Zeiss is Spice parallel. It's a Sandia product that you can download and use. And then when we run it, we get spikes that travel along an axon, as illustrated here. So that's it. Hey, Tom.
This is a question for you and the previous speaker. Have you considered testing these kind of MMISTER architectures on self-organizing learning systems, and how would that be affected by the noise and precision issues? Something like standard competitive learning systems.
Are you talking about like Cahonen, or?
No, just a classic winner-take-all, feed-forward, feedback connection sort of thing.
I haven't done it. There's a lot of stuff that I'd like to get into on that.
But also for the previous speaker, have you done any self-organizing systems with these? You're doing it? Excellent.